Hello everyone, this is Tony Zhao from Soco.ai. Today I'm very excited to share with you on our new progress of incorporating unstructured knowledge source for the future conversational agents. So before I get started, I'd like to briefly introduce myself. My name is Tony Zhao, the co-founder and CEO of Soco.ai. Joining me together is Dr. Q-Sun Lee, the founder and CTO of Soco.ai. And together at SocoDB.ai, we are building a distributed database for natural language. And before that, we obtained our PhD from Canadian Mellon, working on deep learning system for dialog. So let's get started. So today's topic I want to address is about knowledge or knowledge bases for chatbots. For any practitioner or researcher in the dialog field or chatbots space, incorporating knowledge source is essential for any chatbots. To see that, for example, for task-oriented system that actually delivering some task or delivering information to users is always equipped with some databases. For example, it has to look up from database of flights in order to give the real-time flight information to user. On the other hand, for chat-oriented system, knowledge is also important. Research has shown that in order for an open domain chatbot to deliver consistent and satisfactory conversational experience to the user, it has to have some degree of warm knowledge. At the same time, there's also other type of knowledge. For example, the persona knowledge. The bot has to know its own backstory, so it has to keep consistent in its response. So it won't be a woman in one turn and become a man in the next turn. So just to give a little bit more context, even the state-of-the-art deep learning system is still lacking behind in terms of knowledge. For example, the latest paper from Facebook research, the Blender bot, which has achieved significant improvement compared to previous state-of-the-art, for example, dialog GPT, and has achieved almost 50% confusion rate when talking to human. As you can see, lacking of the knowledge about the word and it's one of the most important limitations for the system. So even the system has been trained on billions of data points with such a big model, it still cannot encode in all the knowledge that it should have contained for a proper system. So what type of knowledge source is available for developers to incorporate into their chatbots? We identified there are 4 types of knowledge sources that's available in today's technologies. The first type is perhaps the most understood way is a structured database. Essentially, we're converting the knowledge into a SQL database, and we retrieving them using SQL queries. And the second type is model parameters. And this essentially all the end-to-end dialog models fall into this bucket. For example, the Blender bot from Facebook. By training large neural models on big corpus, the model is able to digest all the knowledge from the corpus and remember them into their parameters. And the solution is very elegant because now one system can solve all the problems, but the limitation is also obvious. It is a complete black box model that is difficult to understand by human, and also, more importantly, difficult to adapt to specific domains. So we can now using this type of approach to make open domain chatbots, but it's still hard to fine-tune them to very specific tasks. The third category is manually curating question-answer pairs. And this approach has been widely used in many customer service automation systems. And then the disadvantage is that really maintaining those question-answer pair is quite hard for human to do, and also because essentially all the answers are limited to those question-answer pairs, having a big list of questions that cover all the problems that can encounter is also a challenge. Lastly, the fourth category is essentially we're providing unstructured text files to the system and hope the system can utilize those information as a source of knowledge. So why do we think text corpus as a knowledge source is a good idea? It enjoys many advantages compared to other ways of encoding knowledge. For example, we deal with documents every day as a human, and it's quite easy for human to maintain a collection of documents that's correct and up to date. And the second, the reason is Actually, because it's easy for human to use and we actually use it every day, we don't have to create knowledge for our chatbots. They're already there in our workspace, in our Dropbox, in our Google Drive. And the third, because for text corpus, it can have a high coverage of knowledge, because this is actually related to the fourth point, because it's very flexible and not limited to predefined schema. As a result, you can encode as many details as possible into the knowledge sources without worrying about breaking your schema of databases. On the other hand, the limitations of text corpus as its knowledge source is also obvious, because in this way, a text corpus is unstructured, and because they are free of schemaless, it becomes quite hard for a machine to understand the meaning and deliver information from it. Perhaps one of the most promising approach is using machine reading at scale, proposed by Denchi in 2017 from Facebook and Stanford. So what is machine reading at scale? So it is a combination of information retrieval and the machine reading comprehension that coming out from the squad dataset. So the basic idea is very simple. Giving a collection of large documents, for example, the entire Wikipedia, and giving questions from the user and the client, we can first retrieve relevant documents from the corpus. And given a list of relevant documents, we apply a machine reading comprehension model on top of that, which will read those documents and extracting answer span directly from the documents as answers. So actually, machine reading at scale style is already being applied to protocol system. For example, we have already seen this type of answer coming out from Google Assistant. For example, if you're asking how to cook pasta to your Google Home speaker, it will be able to find an answer like this. Here is what I found on the web, and then it will be a sentence or a paragraph answer that directly answers a question. And in this case, it found in the steps that using a large pot and load up hot water is the steps to cook pastas. So machine reading at a scale is one of the most exciting research topics in NLP at this moment. In the last few years, since the 2000 initial paper, there has been numerous research following up and proposing new methods to improve the system. And the state of the method has also been improved significantly compared to initial performance. So what are the common challenges that are still remaining in this direction? And we would like to identify the two major categories of challenges in terms of both algorithm as well as engineering. In terms of algorithm side, there are still a number of remaining challenges to be solved. For example, the document retrieval in the first stage is a fixed system, typically a standard PFIDF or BM25 retriever, which bound the performance of the system because they are not trainable. Sometimes they have low recall, and if no answer is getting to the first stage, the second stage, the machine reading comprehension reader can never recover the correct answer. And the second main limitation is it's a single hop system where it has to find an answer in one shot actions. However, to be able to answer complicated questions, for example, who was the father of the founder of Google, for example, often this type of reasoning requires a multi-hop reasoning process, meaning that the system have to going through a number of steps and looking at multiple documents in order to making a decision. And how to enable efficient multi-hop reasoning still remains to be an open research challenge. And then lastly, for inference efficiency. To be able to run the system I show, it becomes very expensive to running all the machine reading comprehension model on a lot of documents, because BERT is prohibitively slow and it's also question dependent, meaning that you have to computing the score for every new question with every document pair, which makes it very slow and prohibitively expensive to be used for real-time applications. On the other hand, in terms of engineering, there has also been a lack of industrial-grade framework that support production-level system. And to scale up this type of the notion of MRS, there are a number of things to have to worry about. The first one is infrastructure. Be able to incorporate the whole in Wikipedia or even more data than that, there should be a distributed storage system as well as a computation system to efficiently digest all this data and making a very efficient index to enable real-time inference. And second, in the research context, the question answering is a very well-defined problem where you are looking for phrase span from text data as answers. However, in real-world applications, it's often more complex than that. People are looking for different level answer at document level, sentence level, or at phrase level. And sometimes you're looking to extracting different type of information more than just one phrase. Maybe sometimes looking for a table and sometimes looking for a summary of the answers. And this is beyond the well-defined self-contained research topic that's usually used in the academia research. So for the rest of the talk, I'd like to give two case studies that we have been working on at Soco.ai. And we have a number of other projects ongoing, and I'd like to share those information in the future. So the first case study we did is Talk to Paper, which is a demo paper at ACL this year in 2020. So the basic idea here is we want to apply MRS to academia research paper. The reason why it's not as important is we all know academic knowledge has been growing rapidly in the last few years. Just using ACL as an example, ACL has grown 140% from 2017 to 2020 in just 3 years. And beyond that, there are more than 4,000 preprints published in arXiv in 2019. It becomes really hard for research to keep up with the latest in research and to know what's going on with the latest trend. And what we did here is we're treating those papers essentially as the unstructured knowledge source and as a text corpus. And we download more than 3,500 papers as a corpus as our knowledge source. And the goal is to creating a conversational system that can answer any questions about research in the last few years. So given the setup, we developed our initial system. In our initial system, our pipeline system, we have introduced a number of innovations compared to the original design from Facebook. First of all, we decided to focus improve the retriever. Instead of using the BM25 system to retrieve a document or paragraph, we decided to develop a neural system that can directly return you relevant sentences that contain the answer. The reason why for that is, for academic research, sometimes we're not only looking for one entity or one term. Instead, we're looking for a sentence or opinion. So in this case, sentence level retrieval makes more sense and providing more context that is understandable by the reader. So in the first stage, as you can see, the system is able to ranking all the sentences in the text corpus, giving a question, and return the relevant sentences. And given many cases, this is already enough. People can already take the sentences, and the chatbot itself can speak back the answer as if they, according to this paper, the author said, but this answer. And optionally, you can still apply the machine reader comprehension model to extracting phrase level answers if that's required. And how do we do the neural ranking system? So in this case, we adopted dual encoder for ranking. So the idea is quite simple. So taking a question and an answer, using two BERT to encode them independently, and using our aggregation function to get a fixed size vector from both sides, which we name Q embedding and A embeddings. And the final score between those two embeddings are computed through dot product or cosine distance. And this enables query agnostic encoding and indexing time, meaning that we can encode the entire corpus of the answers upfront before any queries and saving those vectors into a vector search database. And at query time, we only need to encode the question, and then we can use an approximate nearest neighbor algorithm to enable efficient search to find the most relevant answers. So the results look very promising. So here listing some examples that's actual queries and actual response from the system. And you can see it's able to find really very relevant answers to your question. For example, you can ask him what is LSTM. It's able to find the exact definition, which is a long short-term memory network. And then also you can ask him more subject questions. For example, what is the best system for an AI? And it's able to find one of the state-level method that's being proposed for a natural language inference task. So you can easily imagine this type of system can be incorporated in a conversational manner where the user is asking different type of questions about research, and then the system is able to find real research opinion and giving answers to those questions. So how does it work actually in a more benchmark setting? So we did experiment on benchmarking the neural rankers on 4 different data sets. Those including Squad, natural questions from Google, Marco from Microsoft, and Trivia. And in each data set, we showing the size of the kind of index size, which meaning the number of sentences in the corpus we can retrieve from. And also we're showing the number of queries in the evaluation data sets. And the results is here. And the baseline is a BM25 system from Elasticsearch. And the metric we use is MRR and the recall at 5. And MRR measures the mean reciprocal rank, which is showing how the correct answer is ranked in all the ranking list. And the recall at 5 means that among the top 5 answers, if the correct answer is in there. As we can see, the neural ranker is able to achieve significant improvement on all the datasets compared to BM25. And you can see the biggest improvement is actually achieved on the natural question and the Marco. The reason why behind that is in the Squad and Trivia, we found that there's a high overlapping between words in the question versus the correct answer. And the meaning of that, the reason of that is because the question asker from those corpus, actually they know the correct answer when they generate the question. And for the 2 bottom corpus, natural question and Marco, they are actually real queries from search engines, so that the user don't know the correct answer. So that in the query, it has very little overlapping compared to with the actual answer in the text. Now I'd like to switch topic a little bit and go into the second topic, which is the SocoDB that we are building at Soco.ai. As we talked previously, the challenges including both algorithm side as well as engineering side challenges for making this type of system into production. And what we're building at Soco.ai is a distributed database for natural language. And it basically solves the problem of storing a large number of text data and also reason the contents using the MRC model and distill knowledge. And it can be used for intelligent search, question answering, information extraction, and text analytics. What does that mean exactly? Here I'm showing a pipeline graph for what does it look like for a distributed database for MIS and beyond. Essentially, by storing in the storage layer, it will contain all the data documents that you can uploading that you can have, and then the Soco core will automatically process them in the background and indexing them using neural indexers as well as machine readers. And this allows the developers to asking questions just as if there was structured data. For example, you can ask, what country does this credit card offer Visa coupon for? And it's able to find the document that contains the answer and give you a highlighted phrase span extraction that tells you the exact countries that has those numbers. So this is only one example of how to using SocoDB. You can actually doing other queries. For example, you can looking up the person and also at the same time request its birthday and job titles. So you can see that multiple piece information has to be grouped together in this query, and the system will be able to find the SocoDB will do this in the background to find the relevant documents and sort out the information requesting. So to compare with other existing databases, the one is MongoDB, which is a very popular NoSQL database. and it's designed to storing semi-structured documents, and you can doing filters just like normal databases. And the second comparison could be Elasticsearch, which is also a very popular search engine. In their case, they're also indexing free text semi-structured JSON documents, and you can doing a BM25 based full text search. And compared to SocoDB, and it is designed to processing raw documents directly, so you don't have to convert into JSON, but you can. And then also it's able to use machine reading at scale to find precise answers, giving natural language queries as well as structured queries. And it's also get equipped with other deep learning native models, so that it's really easy to plug in to your own TensorFlow PyTorch model in order to support all the latest function that you want to have powered by NLP systems. So I'd like to give two examples about actual use cases. So one use case is SocoDB has been used to improve the customer service for one of the top banks in the world. So what it does is the SocoDB is synchronized with all the product documentations and historic emails from support agents. And also it is equipped with the latest version of the credit card information as well. And we know the credit card information is a very timely information, so it has to keep changing from quarter to quarter. And this becomes quite a challenge for the previous team to develop chatbots, because if you equip with training chatbots using the slot filling approach, many of the fields has to change over time, and also you have to keep the database up to date, which sometimes invalidates the state tracking. So given that, by using SocoDB to indexing all the documents in real time and enable real-time question answering to the support agents, the support agent is able to find the right answer to the customer much faster compared to before. And we already observing a 30% reduction in terms of ticket resolution time. A second use case we have been building for our customer is combine the SocoDB as a part of a multi-turn dialog agents. So multi-turn dialog agent is really useful for many cases, because sometimes it's just impossible to find the right information in one query. And often you have to do going through your dialog policy to asking a number of different criteria in order to issue a query to the database. So you can do the same thing for SocoDB, and essentially the difference is you still have the normal dialog pipeline where you have NLU, the dialog policy, the dialog manager, and an NLG system. And you, by asking all the required questions, for example, in this case, you're asking for the department number and then what the user group the user belong to. And after those slots are issued, you can have using a template approach to generating a pseudo natural language query. For example, the goal is asking for what is the phone number of this department for this user group, for example. By issuing this query to the SocoDB as an unstructured form, it will return the answer as I showed in the previous cases, and it will find the phone number quite accurately from millions of documents. And after the contextual DM gets the answer, it can do the post-processing and converting them to a verbal action going back to user. Just as if the Google Assistant example, where I can say, oh, I found this information and found information for you, and the phone number is this number and the source is this document. So in conclusion, we have covered 3 topics in this presentation. First of all, we talk about 4 types of common knowledge sources and a potential way to using text corpus as a knowledge basis. And second, we talk about a neural ranker approach that is being applied to academic paper search and improving results significantly compared to BM25. And then lastly, we're introducing SocoDB, a distributed AI database for enabling MIS for production usage. And we also may talk about 2 applications that are being applied to customer service and multi-turn chatbots. Thank you very much, and this is the end of my talk, and Q-san will be able to answer any question you may have. Thank you.